Class, we're now doing lesson 12-2. You perhaps would like to be on page 771. We already have the necessary pictures on the boards. Before we start, we're going to have to get some terms or definitions out of the way. Chord. Something like this is a chord. A segment with its ends on the circle. We're talking chord? That's what I mean. Then we're also going to be talking about central angles. We've had that before. Those are angles with their vertex at the center. And then another term I'll be slinging around is intercepted. Notice how this angle catches arc CD. I'll probably just say it intercepts arc CD, and you'll know what I'm talking about. Take a look at theorem 12-4, and I'll have my assistant, JC, will read the first part of that theorem 12-4.
Within a circle or in congruent circles, congruent central angles have congruent arcs.
This is what she said, really. She said if this angle is equal to this angle, that means this arc is equal to this arc. And that works if you have two of these angles on the same circle, or if you have same size circles, you could do it with two different circles, but then they'd have to be the same size. I feel like that one's kind of intuitive, instinctive. You probably would have guessed it to be true. So let's go to some, wait, is there a second part? What is that?
Within a circle or in congruent circles, congruent arcs have congruent central angles.
Do you know what she just did there? She just said it works both ways. If you know this, then you got this. Or if you know the arcs are equal, that means the angles have to be equal. That one's not hard. Derek, let's take them on to 12-5. We'll have Samantha read that one.
Within a circle or in congruent circles, congruent central angles have congruent arcs.
Is that this one? Olivia, this one? Is this the one you drew?
No, I drew the first one.
Caleb drew that one, that's it.
Oh, okay. This is 12-5? Okay. Because he didn't label it. We can criticize him because he's not immediately present at the moment. All right. Samantha said that if the angles are equal, then these chords are equal. Is that what it said, Samantha?
Yeah.
Does this one have a flip side also?
Mm-hmm.
Well, can you run it the other way then?
Within a circle or in congruent circles, congruent chords have congruent central angles.
So that one's not that deep either. If you have congruent central angles, they will intercept congruent chords. If you see two angles intercepting congruent chords, then they must have been congruent angles. Let's try to find something a little more exciting here, Julia. What's the next one about?
Within a circle or in congruent circles, congruent chords have congruent arcs.
Oh. I think Julia is saying that if these two chords, A, B, and C, D, if they're congruent, then these arcs that they intercept or catch are also congruent. Julia, is this one reversible?
Yes.
Oh, we'll read it back the other way then.
Within a circle or in congruent circles, congruent arcs have congruent chords.
Uh-huh. So if a chord is a certain length, that determines how big of a arc it catches. So if you have two of them the same, they'll catch the same arc. And it works both ways. 12-7 is looking a little more exciting, Lauren. Will you read 12-7?
Within a circle or in congruent circles, chords equidistant from the center or centers are congruent.
Ah. this is what Lauren is saying. Say hi to Aaron.
Hi, Aaron.
Lauren is saying in 12-7 here that if these chords are the same far out from the center, in other words, if those segments are the same, because that's where you would measure how far out they are from the center. If they're the same far out, they'll be the same length. Can you see that the further out they are, the shorter they would have to be? So if they're the same far out, they're the same. Does this one have a flip side to it, Lauren?
Yeah. Within a circle or incongruent circles, congruent chords are equidistant from the center or centers.
So she's saying not only does equal far out make equal chords would have to be equal far out. I could walk back to this other picture, and just because of that and that, I could go right on here and go, Remember, distances or how far to a segment have to be measured perpendicularly. It would be silly to do anything else. 12-8. You see 12-8? It must be
Guessing
that
it's
one.
that one.
All right. Let's ask Kinsley will read 12-8.
In a circle, if a diameter is perpendicular to a chord, then it bisects the chord in its arc.
If a diameter is perpendicular to a chord, like this picture, then it bisects the chord and the arc. Kinsley is saying that since this chord goes through the middle, making it a diameter, and it's perpendicular to this chord, that means bam, bam, and bam, bam. All right. Is there more to this one or not? That's it, right? So that was 12-8. Where's 9? Oh, that's 9. Connor, could you read me 12-9?
In a circle, if a diameter bisects a chord that is not a diameter, then it is perpendicular to the chord.
Ah! It's sort of part of the other one backwards. He's saying if the chord goes through the middle, making it a diameter, and if it bisects like that, it's got to be a right angle. Got to be. So if you have this and you have that, then that must be true right there. They're starting to get good now. I think there's one more. Could you read it, Molly? Is it 12-10?
In a circle, the perpendicular bisector of a chord contains the center of the circle.
What she's saying is that if you have one chord bisecting another chord perpendicularly, then it goes through the middle and makes it a diameter. If you have this and this, then you may now assume that. This one's going to be useful in a construction we're going to do later today, where we figure out how to find the missing center of a circle. Let's sign off right there, Derek.